Welcome to Generative AI Futures. Today, we're diving into a paper that takes a sledgehammer to one of the core assumptions in modern AI, something that for almost 10 years, everybody thought was absolutely essential. We're going to see what happens when you pull that cornerstone out.
So imagine this. For years, a specific building block has been in basically every deep neural network you can think of. It was considered totally non-negotiable. But what if it was all just a big misunderstanding? Well, a new paper from Meta AI is challenging that exact idea, and they're suggesting we might not need it at all.
All right, so let's get into this established dogma. The component we're talking about is normalization layers. If you've ever built or trained a model, you know these things. They're everywhere, and they've always been seen as just as fundamental as the activation functions themselves.
And this isn't some new fad, right? We're talking about a whole decade of dominance. It really kicked off back in 2015 with batch norm, which completely changed the game for computer vision. A year later, Layer Norm came along and pretty much became the gold standard for transformers. And even more recently, you've got RMSNorm, which is a simpler version that's used in huge models like Llama. The consensus has been absolutely clear. If you want to train a deep network, you need normalization, period.
So, what is this thing actually doing under the hood? Well, this formula right here is the heart of it. Let's break it down real quick. First, you take your input x and you subtract the mean, mu. That centers all your data around 0. Then, you divide by the standard deviation, which is just the square root of the variance, sigma squared, and that scales everything down. It kind of tames the data into a nice, stable distribution. But then, and this is key, it uses two learnable parameters, gamma and beta, to scale and shift the data back again. This gives the network the flexibility to undo the normalization if it needs to. And for years, we believe this whole dance was essential for stable training.
But here's where things get really interesting. The researchers behind this paper, they started by asking a super simple question, a question that ended up uncovering a hidden secret about what Layer Norm is really up to. Instead of just accepting that it works, they decided to just look at it. They asked, hey, if we plot the values going into a Layer Norm layer against the values coming out of it, what does that relationship actually look like? The answer was definitely not what anyone expected.
And the result was, whoa, it wasn't a straight line, which is kind of what you'd expect from something called normalization. Instead, the plot formed this beautiful, distinct S-shaped curve. It looked almost exactly like a hyperbolic tangent function, or tan. What that tells you is that values near the middle are pretty much left alone, but the extreme values, the big outliers way out on the ends, they get squashed.
And hey, don't just take my word for it. The researchers themselves were kind of blown away. They wrote in the paper, and I quote, "It is still surprising to us that the actual nonlinear transformation is highly similar to a scaled tanh function. This was a genuine, that's weird, moment in research."
So how on earth is this possible? If you look at the math for just one input, a single token, the operation is perfectly linear. But here's the clever bit. Layer Norm calculates a different mean and a different variance for every single token that passes through it. So you've got thousands of these slightly different linear operations all happening in parallel. And when you plot the collective result of all of them together, you get this emergent nonlinear squashing effect. It's a classic case of the whole being greater than the sum of its parts. This incredible observation led to a solution that is just so elegant. The thinking was, okay, if Layer Norm is just accidentally behaving like a tanh function, why don't we just use a tanh function instead? And just like that, Dynamic Tanh, or DyT, was born.
And here it is. This is the entire replacement. Look how simple it is. It's an element-wise function. You take your input x, you multiply it by a new learnable number, alpha, you run it through a standard tanh function, and then you apply those same gamma and beta parameters we saw before. That's it. No more calculating means, no more variances. It's designed to be a direct drop-in replacement.
Let's just pull this apart for a second, because each piece here is doing a very specific job. The tan checks part, that's obvious. It provides that core S-shaped curve, the squashing effect that we saw Layer Norm was doing by accident. The gamma and beta parameters, same as before. They just scale and shift the final output. But the real secret sauce, the magic ingredient, is alpha. This single learnable number is the dynamic in Dynamic Tanh. The network learns the perfect value for alpha to scale the input before it even hits the tanh function, which lets it control exactly how aggressive that squashing should be.
Okay, so the theory is beautiful, right? It's simple, it's elegant, but the big question is, does it actually work?
So the researchers put DyT through a trial by fire. They took a whole bunch of state-of-the-art models and just swapped Layer Norm out for DyT to see if it could hold its own. Let's start with computer vision, using the classic ImageNet benchmark. Take a look at these numbers. Whether it's a vision transformer or a convext, DTY doesn't just match the performance of Layer Norm. In almost every case, it's actually a little bit better. It's winning. And this chart right here, this really highlights the biggest win. On the VIT large model, just swapping out Layer Norm for DyNorm boosted accuracy by a full 0.5%. Now that might not sound like a lot, but in the world of highly optimized state-of-the-art models, a 0.5% gain from such a simple change is a huge deal.
But is it a one-trick pony for vision models? Not at all. Look at this table. It shows how robust DIoT is across a crazy range of tasks. For self-supervised learning, it's right on par. For diffusion models used for image generation, it actually improves the score. And for a 7 billion parameter llama model and a wave-to-vec speech model, the training losses are practically identical. The takeaway is crystal clear. This thing just works everywhere.
Okay, so we've seen that it works. Now for the million-dollar question, the one that really matters. Why? Why does this simple little function work so well? What is that dynamic scalar, alpha, actually learning to do?
This right here is the key insight. The researchers analyzed what value alpha was settling on during training, and the answer is just so cool. It turns out that alpha learns to be the inverse of the standard deviation of the input, 1/sigma. In other words, this one tiny number learns to do the scaling part of normalization all by itself, but in a much simpler, more global way for the entire batch of data. It's self-organizing normalization.
And this ablation study really nails it down. Basically, they started taking the DyT function apart to see which bits were essential. If you get rid of the tanh and just use a linear function, the model completely fails to train. It just explodes. So that nonlinear squashing is critical. But then, if you keep the tanh but get rid of the learnable alpha, performance drops by a lot. You absolutely need both the dynamic scaling from alpha and the squashing from tanh. They're a team.
Now, to be clear, people have tried to get rid of normalization before. There are methods out there like fix-up and skip-init, but honestly, they often come with a pretty big hit to performance, and they require a ton of careful, model-specific tuning just to stop the training from failing. DyNT, on the other hand, just works. You can drop it in right out of the box, and it consistently matches or beats the baseline with little to no extra effort. It's just a much more practical and robust solution.
Ultimately, this research forces us to step back and reevaluate the things we take for granted. It shows that layer normalization wasn't important for the reason we thought it was. Its real contribution was an accidental nonlinear squashing effect, which, it turns out, can be done much more directly. And that just leaves us with this one massive, exciting question. If a pillar as fundamental as normalization can be replaced by something this simple, what's the next essential piece of AI that's just waiting to be knocked over?